All right, motion control layout. What is it? It's basically using a whole quadrant of the ball that we haven't been using. The mid 80s, when two-piece balls became a thing, and when I started drilling balls, basically you had your pin and your CG. They weren't usually out that far back then, but nonetheless, your pin, your mass bias, and the pin was always somewhere up around the finger area because we need the ball to flare around the fingers, so you're moving the bow tie up. And then your CG, your mass bias, is always down somewhere in this area, right? And if you wanted a weight hole, you always put the weight hole in it because you had to have, you take the weight out of here. So the weight holes were always in this area, so it would be legal. Well, we don't have that anymore. So what a motion control layout is doing that. So we're putting the mass bias actually up in the finger quadrant above the axis point and not below it. And I'm going to explain to you why that's going to make a big difference in the reaction of these balls. So let's go over a couple traditional layouts, and then I'll show you what a motion control layout is, and then I'll show you how to lay a motion control ball out. So this is a 4x4x2, pretty standard. You get all your measurements in there, down over, and you find the center of your grip. Dual angle layout. This one is I did 50 by 5 by 60, so you get everything all lined up, over, down, center of your grip. And this is where that's just where you're going to be, okay? With a motion control layout, what you're going to do is you're going to set an angle, and you're going to have your arc with however far you want the pin out. This one happens to be 4 inches. But with what we can do on these that you cannot do on these is, as long as your axis is based off of anywhere on this arc, you can move the pin up and you can move the pin down. So that's a big bonus of these. And let me show you dynamically what happens with these. So if this was your ball track, and this is your axis point, and this is your mass bias, every time this ball rotates, it's trying to balance itself. That's what track flare is. So as it rotates and the axis keeps moving, the axis is moving toward the mass bias, okay? Because the ball is flaring away from it. So everything is flaring this way. As this gets closer to this, the ball becomes a little more stable every rotation because it's getting closer to its goal, its preferred spin axis, and because it's getting closer to it, it becomes a little bit weaker. So as this ball is going through the front of the lane and flaring and doing all the stuff it needs to do, you're still in the head, you're still in the oil, and it's doing everything it's supposed to do. It is becoming slightly weaker on each rotation. And then that means the closer it gets to the head pin, it's still getting weaker and weaker because it's going to continue to flare. So that's what happens when you're dealing with the way we've been drilling balls for 40 years. With a motion control layout, you got your ball track, the angle we predetermined with our measurements, the pin height we determined by where we wanted to put it, and you have your axis point. So every time this ball turns over, your axis is moving away from the mass bias, and your track, which is the point of contact, is moving towards your mass bias. So it's doing this, okay? Now here's why this is effective. If we did the same core distance on both of these balls and you put one exactly opposite with these exact angles below instead of above based off of these coordinates, this ball will get through the front of the lane faster than the one down here would, because core is doing this, right? End over end as we throw it. But the core is also doing, if this is your mass bias, okay? And this is your ball track. And you got your ball drilled like this. As it rotates, it does this. The track goes away from this. And the axis is getting closer to it. That makes the ball become dynamically stable on each rotation, more stable, okay? And that's just what they do. But when you're dealing with a point of contact, so this is our mass bias, but we're at this angle, all right? So each time this ball rotates, the mass bias is getting farther from the axis, closer to the track, all right? Well, why should that make much of a difference? They should react the same. Here's why they won't. We'll use this again. When your mass bias is getting closer to your axis point, it's doing this because it's getting closer and closer to where it wants to be. So it's stabilizing itself, okay? When you're dealing with a motion control layout, Since the mass bias is going to the track and not to the axis, it goes like this. It gets wider and wider, okay? So each time this ball turns over this distance, the mass bias is traveling around a smaller circumference of a smaller amount of the ball. Smaller and smaller and smaller, okay? One of the reasons it can achieve its goal faster. On a motion control layout, the mass bias, each time it rotates, is farther from the axis of rotation, closer to the ball track, so the mass bias has to travel farther on this rotation than it did on the last rotation. And on the next rotation, it has to travel even farther. And on the next rotation, it has to travel even farther. And because of that, it takes this ball longer to achieve its goal, which means it retains energy longer and can create much more angle of entry on the back of the lane. And the versatility of being able to move the pin up or down anywhere you want. So let me show you how to lay one out. All right. First, and again, mass bias, symbol or asymbol, it doesn't make any difference. So our requisite line, all right? So I want the pin 4 inches off my axis. All right, so I'll make my little arc without breaking the pencil. Oh, that's rare. All right, so I know that as long as my axis is based off of anywhere on this arc, that this pin will be 4 inches off my axis. Now, the axis we're going to be using today is 5 inches over and 1 inch up, okay? So what I need to do is find the axis angle, okay? Let me show you what that is. So anywhere on the ball, let's find an axis, okay? So our axis is 5 inches over. So right here, and we go 1 inch up right here. All right, so this is the center of our grip. This is our axis point. Now draw a line from the axis point to the center of the grip. And this angle right here is what we need to know. So center of your prosect and the center of the grip. Turn it so y'all can see it. All right, and if we look, we're at 15 degrees. Huge important number, 15 degrees, all right? So, if we drilled this straight up and down, 0 degrees, and you just went 5 inches straight over, boom, okay, center of your grip. So if we just drilled it like this, that would be 0 degrees. That is not 0 degrees, that would be 15 degrees for this individual's axis point because he's 5 over an inch up, which creates that 15 degrees. So his ball track would not be like this, it would be like this. That's where the 15 degrees is. So when you're determining what angle you want to put the mass bias line on, you have to either, if it's their axis is over and up, you have to subtract that amount. And if they have an inverted axis, say there's 15 degrees built in, so if I turn this to 15 degrees, it would be at 0. I have to subtract 15, okay? Or I have to add 15, I'm sorry. Inverted, you have to add it because you need to go more to make up for it. So for example, we're gonna do this one at 45 degrees. So what I'm gonna do is I'm gonna place the center of the prosect, the center of the pin, and I wanna do 45 degrees, but 15 degrees are built in. So we're gonna go to 30 degrees and make our line perpendicular to that line. Oh. We're not going to. Stay with me. Yeah, this works for left-handers too. Ugh. We're going to 30 degree that line. Okay, so you line it up, do it at 30. This line right here, perpendicular it, is that a word? Okay, this line right here is going to be parallel to the center of the grip line. So for simplicity, this line you're done with, and this line you're done with. Don't need them. All right, so that's where we're at right now. This is going to be at 45 degrees. The pin is 4 inches off the axis. Now the bonus with this, one bonus, is because we measure over and down and not over and up, I'm going to make sure that my 5-inch mark is anywhere on this arc I want. So as long as I put the grip line parallel to this line, and this is at 5 inches, I can put the pin anywhere I want, which is a big advantage if we're trying to fine tune reaction. So let's just say that we're gonna go right here. So I'm gonna go 5 over, make my center line. Here's my center line. And remember, he's an inch up, so we're going an inch down. And right there is the center of your grip. And it's as easy as that. It's the difference in reaction is absolutely amazing how much more you can get a ball to hook on the back of the lane that's not really designed to. There's countless variations we can do with layouts, and in my next video, that's what I'm going to go over. I'm going to show you some different examples of layouts we've tested, layouts that I use personally, that I just find they're just fantastic. So this layout works on symmetrical balls or asymmetrical balls, cores, I misspoke. And it also works really well with no thumb guys, two-handers. The only thing you obviously have to pay attention to is with a no thumb person, you have to get the pin up to get around the fingers, the ball flare. So you can't have more than 3 ounces of top weight if your CG is going to be straight on the side of the ball. So keep that in mind. I know most of the balls that come through my shop, they're right around 3. I think the manufacturers are trying to do that for this reason. But it works for anybody. So you're having everything chase each other instead of roll away from each other. And as that thing gets, it just takes longer for that to happen. So that's kind of a basic breakdown of what a motion control layout is, what it's going to look like when you drill it, why it works. We'll start going over different layouts in the next video. I appreciate it watching. And oh yeah, like and subscribe. Thanks.